All right, welcome everyone to lecture number 2 in this Introductory Signal Processing course. Again, my name is Nathan Kutz, and this is going to be a course that introduces basics of signal processing using MATLAB and Python as our software components to do a lot of the signal processing for us. The second lecture is going to simply talk about some of the basics and setting up some of the mathematical architectures we're going to need on the basics of signal properties. So most of what we're going to look at is signal processing is about transformations, taking signals, transforming them into a little bit easier ways to process or understand those signals. And we have the mathematical capability to do these signal processing operations once we understand some of these basic ideas here. All right, so signal processing, the entire goal is to control the transformation of that signal into something that's more meaningful for us to be using typically in some kind of technology architecture or technology stack. So the way to think about this mathematically is here, where we're taking the signal itself, undergoing a transformation or a series of transformations to produce a signal that we can use to either make decisions or control decisions on some technology or produce a signal that is easier for us to understand in terms of whether it's a scientific application or giving it more meaning. We want to be able to control this process. We can do this with a continuous time signal or a discrete signal as well. So we're going to be thinking a lot about what goes on in here. Again, what kind of operations can we do to a signal to produce something a little more meaningful for us at the end of this? And if you remember from the first lecture, we think about taking signals, whether they're signals that come from the electromagnetic domain, hitting on our sensors, bringing in information that we process out, or acoustic signals, or both. And we may have a bunch of signals coming in, allowing us to make some decisions to get out something more meaningful at the end of this process. So before we really dive into all of this over the course of this set of lectures, we want to start thinking about basic properties of these signals and basic kind of operations that might go onto these signals. So let's start off with the most simple thing, which is time shifting. So we're typically going to take something like a continuous signal, and time shifting, for instance, allows us just to simply take that signal, shift it over by a prescribed amount of time in a t naught, and so now we have the same signal just shifted over in time. And sometimes this is really important. For instance, if you have a delay in a signal and you want to synchronize signals, you might have to delay some of the signals all in the right amount to get them into the right time bins together, okay? Happens in discrete time or continuous time. So in discrete time, it's some shift by some number of n, right? So remember, n is the parameterization. It acts like the time variable, and so we want to shift this over. And so these are one of the basic operations that we would have in either discrete time or continuous signals. Just an example, here is a signal, discrete signal, x of n, and we're going to shift it over by some n naught. So you can totally see what's going on here. You take this signal here, and here's, let's say, a point we want to concentrate on. And notice this thing here gets shifted over, and this is your n naught. So that is the shift that we have, and all we did is move the entire signal over, right, by this amount here. Okay, so that's the idea behind the shift here on a discrete signal. Same thing with a continuous signal. We can shift this thing, and you can see here's this peak that we're looking at here. And if we shift it over by some t naught, then that's that t naught right there. So we can prescribe time shifts very simply by taking that signal and shifting its origin of time. That's ultimately all this does, right? So these are very common operations to be doing. They're pretty simple to put together, but oftentimes what this allows you to do by allowing you to shift the time origin is maybe you have a diversity of signals that you need to align in time because some have latencies with them. This is a very simple way to shift those to get all the latencies correct. Okay. Time shifts can also be included with more broad kind of objectives. And in fact, here what we've done is not only going to time shift, but we're also going to potentially scale time, so stretch time or compress time in this very more general architecture of a very simple operation to be doing to our signal. So for instance here, our signal alpha, our alpha here is a parameter which allows us to stretch time, whereas beta is our time shift itself. So what alpha does is it takes our signal, and if alpha is less than 1, then what it's going to do for us, it's going to stretch time. Okay, so it's going to take a signal that maybe is very tight in time and stretch it out. Whereas if alpha here is greater than 1, then it's going to allow us to do a time compression. So we can both do these two operations all within one generic framework, which is this here, right? So this is our generic framework for taking signal, both moving it in time and then stretching it or compressing it, however we desire to manipulate that signal. Okay? So for instance here's what a scaling looks like. So what you're looking at here, here's x of t. Here is this thing scaled, so you essentially compressed this by a factor of 2. So if I look at this signal now and put instead of x of t, x of 2t, so now it's going to essentially happen twice as fast in time, and so this scaling law helps us to compress the signal. If I do t over 2, in other words, I slowed time down, so for the same unit of time, now it happens in twice the time bin, this is what you get here. This is a stretched signal. And there's various reasons why we might want to do all of this. It could turn out to be that what we want to do is, again, is synchronize different sensor measurements all to be of the same time, whereas if they have different measurement rates, you want to make sure to scale them all to be synchronous together. So this is scaling is a very important operation to go along with time shifting. And by the way, we're very familiar with this from the point of view of our cosines and sines, things that we have traditionally worked with in signals, which is here is a very simple representation of this from going from cosine t over 2. You can see I have this slow signal, one period over the same time bin. Cosine t now has 2 oscillations over that same time bin. So essentially what I've done, I've sped up time, or I've made this thing compressed. Cosine 2t gets compressed yet again. Cosine 3t compressed even more. In fact, if I take a continuous time signal, and if I just keep increasing this integer, I'm going to get higher and higher oscillations. In other words, I'm compressing these oscillations into shorter and shorter time bins. Okay? And if I go the opposite way, instead of t over 2, I get t over 4, then in fact I am in stretching time. Okay? So we're pretty familiar with this, right? We just, and again, we're familiar from it from the point of view of we've often worked with sines and cosines, but really this idea of stretching, of having different frequency content, that's another way of thinking about these stretched time or compressed time variables. We've always had this intuition of it in terms of cosines and sines, and now we're going to broaden it to just generic signals. Okay? All right, so that's one kind of operation we want to think about. There are other properties and other things we might want to do. So one of these is called reflection. So reflection is very simple. You're going to take time t and you're going to make it negative t. So what it looks like forward in time, you're going to make it look like that backward in time. Okay? Same thing with discrete n should be equal to x minus n. So one way to think about it is you are creating a signal that is even in time. So whatever it looks like in the future is going to look like in the past. And so this is an operation that enforces this. So you take a signal, you can flip it so it has its reflection. So here is how you reflect this signal. So for instance, here's a discrete time signal. There it is. And notice what you're going to do here. This is x of n is 0. If you're going to say that n in 5 has to be n negative 5, you're going to flip all of these over here and you'll reflect them around that x equals 0 axis. In other words, you're going to flip everything around this axis here, and here is your new signal that just got reflected. So everything over here gets reflected over there. Everything that's over here gets reflected over there. Okay? So that's a reflection operation that we can apply to a signal. Same thing with the continuous time. You're going to flip about this axis right here. So this peak here is going to end up over here. In fact, this whole signal then gets translated over to here. And so you just flip it about that axis. So this reflection that we're going to use. Remember, all the signal processing is going to be composed of all these very basic operations. So we're going to take a signal, we want to do simple things to it, maybe many simple things to it, and then eventually get out a signal that is very useful for us for whatever application we have in mind. Okay, so these can also be composed. So compositional operations. Here is a set of operations we can apply to an original signal here. Here's some x of t. Turns on at time 0 to 1, and then it comes off to time 2. And here's the first operation we want to do, which is shift it over by 1. So you're going to take this entire signal, and we know how to do time shifting, and so we just shift it over by 1. So that's the first operation, time shift. Then we're going to reflect. So after I time shifted it, x, I'm going to take t to minus t, and so now I get this new signal, x of minus t plus 1, which is you just reflect here around this axis, and so now here is your new signal. So first a time shift, I shift it, I now reflect it. After I've reflected it, we're going to scale it, so t goes to 3/2 t, and notice what it does is it takes this signal and compresses it, and notice I've got it back now to positive value, so I've flipped it back as well. So I reflected and flipped and got this thing to this signal, and finally shift it once again by 1, and here's the final signal. Okay, so all this is meant to do is illustrate that you can apply these different operations to the signal in order, and you get a new processed signal at the end of this thing. All right, so let's talk about other kinds of signal, periodic signals. This is probably one of the most important pieces of what we want to do here, because mostly what we're going to be working with is periodic signals throughout this course. Periodic signals are the ones that extend over a very long period of time. So we have continuous signals, here they are, that have some period p. What we want to understand is how do we calculate that period p and create these periodic signals. So x of t plus p. So you get the same signal back if you shift it over by p. Now you're already familiar with this from sines and cosines. So if I take a sine and a cosine and I shift it by 2 pi, I get back the same sine and cosine. So in fact, sines and cosines are going to be one of the canonical functions that we work with throughout this course, because they are one of the functions that persist and live at plus and minus infinity without blowing up or going to 0. And they have a nice periodic structure of 2 pi. We can also do this with discrete signals, where n is the underlying shift that we have here, which is the period. So if I shift it over by n slots into the future, it should give me the same signal. So for instance, here's a periodic signal. And this is just a signal, it keeps repeating itself. And amazingly, Fourier analysis, which we're going to use quite a bit of, says that I can represent any periodic signal as a sums of sines and cosines. And this is going to be the foundational to signal processing, is this idea that Fourier proposed, that you could do this with any signal, even signals like this that clearly do not look like sines or cosines. So we're going to show how that happens as we go along in this course. And we're going to make use of that throughout this course, which is we're going to take these signals, process it, and that underlying frequency content that we get out of the sines and cosines is going to be part of our signal spectrum. And so we can do all kinds of operations then on the frequencies, including filtering or shifting, whatever we need to be doing to pull out signals of interest to ourselves. That is a continuous time signal. Let's talk about discrete signal. Here's a discrete signal that's periodic. So it's up, up, down, so forth. So, this is just a different version of what I just showed you, but it's clearly a periodic signal. And if you shift it over by n equals 3, then if you started here, you would end up here. Start here, you end up here. Okay? So these are just 2 example signals that we have to work with. In addition to having these signals, we also can think about having even and odd signals. So periodic signals, even and odd signals. What is an even signal? An even signal that is that if you go to x of t, it looks the same as x of minus t. So this looks like our reflection property that we talked about, but this is just part of the signal. A reflection is just I could take the signal and reflect it. What this says is I took a signal and it has this underlying properties. And in fact, we already know what even a signal looks like. It's, for instance, a cosine has this property. An odd signal is when you go x of t to minus x of minus t. Here it is. Not only do you go backwards in time, but backwards in time, it's the opposite sign. The signal has an opposite value there, okay, a negative value. And those are like our signs. So we already have some base signals that we know have even and odd properties. And cosines and sines have these, but also we can just generically define it more broadly. They don't have to be cosines and sines, although those are the signals that we are perhaps most familiar with. Okay? Again, examples. Here is an even signal right here, right? So you just reflect about this axis. Here is an odd signal. You reflect about this axis and switch the sign. So if you reflected about this axis, it'd be up here, but then you now flip it about this axis, it's down here, and that is an odd signal. So whatever happened here in time, it's the opposite sign here in negative time. Okay? So even and odd signals, these are ways to characterize our signals. So we're going to characterize signals as being things like, oh, it's a periodic signal that's even, or a periodic signal that's odd. Or we can even do things like think about pulling out the even and odd parts of a signal. And here's how you just do this. You can take any function and take its even part by saying take the function itself, take this signal that we have, take it, add it to x of minus t, divide by 2. This will be the even part of the signal, and that's represented here by this, what this e on the signal does. This is the even operation on x, which pulls out the even part of the signal. If you want the odd part of the signal, which is denoted by here, you take that signal and you subtract x to the minus t divided by 1/2. And by the way, these formulas, we've done this before with sines and cosines in terms of representation, in terms of their complex representation as e to the I omega t. Okay? And so if you remember that cosine is e to the I omega t plus e to the minus I omega t over 2, and a sine is e to the I omega t minus e to the minus I omega t divided with 2i. So these formulas are ways to get out even and odd functions generically for any signal. So just as an example, consider this signal here, right? This is zeros and it comes on here at 0. So this is a signal we might want to consider, and you could ask the following question: what is the even part of that? What is the odd part of that? And so if you wanted to take this signal, it's easy enough to take this signal and add it to its negative component, okay? And this is what you get. Or take that signal, subtract its negative component, this is what you get. So this here is the even part of that signal right there. Here it is, okay? And this here is the odd part of that signal. So notice it's even because it's the same on both sides. It's odd because here this is the negative of this side. But if I add these two together, I get exactly this here. So again, this even odd decomposition, I could always represent this as a sum of cosines because it's even. I can always represent this as a sum of sines because it's odd. Okay, so these are just generic properties and things we want to think about in signal processing. So you saw here that basically, we want to start thinking about characterizing signals, and we characterize them by looking at different properties, whether they're periodic, they're even, they're odd, things like these reflection properties, time shifting, scalings. These are all the things that are going to be sort of the baseline operations that we're going to have in signal processing. So now that we've introduced them, we're going to start building on them more and more over the course of the lectures that we have, and so we'll frame up a very robust framework for being able to take signals in, process them out, and giving us meaningful signals at the output.